Going to do the Lewis structure of the nitrate anion, determine its molecular shape, and show you the possible resonance structures it may have. First thing we do, the steps to doing a resonance structure are here on the right. First thing is count the number of valence electrons. So nitrate is NO3 minus 1. So N has 5 electrons. Oxygen has 6, but there are 3 of them. And then because it's negatively charged, we have an extra electron. So that is going to be 5 plus 18 plus 1, 24 electrons. Assemble a framework with 2 electrons per bond. I'm going to put the least electronegative, which is often also the least abundant element, in the middle, and that is nitrogen. Oxygen on the outsides. And I'm going to put in some covalent bonds. Each bond holds 2 electrons. There's 3 of them, so it's minus 6. That means I have 18 electrons left over. So the next step is to fill in the outer atoms for a total of 8 electrons for an octet. So each oxygen will get 6 electrons. Done that, and now I've used all the electrons available. Now I need to fill the inner octet. Now I don't have any electrons left over, and nitrogen only has 6. So when you run out of electrons and you have not filled the octet of all the atoms, what you do is you borrow from one atom, like I did here, from this oxygen, and you create a double bond. So now nitrogen has an octet, 2, 4, 6, 8 electrons. Each of my oxygens has an octet, 2, 4, 6, 8. And then the one with the double bond has 2, 4, 6, and 8. Now we need to optimize with formal charge. The formal charge of my nitrogen is going to be equal to the number of valence electrons, that's 5, minus the number of bonds, that's 4, minus the number of unbonded electrons, there's 0. So that's plus 1. I have 2 different kinds of oxygens. The one with the double bond has a formal charge that will be the number of valence electrons minus the number of bonds, that's 2, minus the number of unbonded electrons, that's 0. That's good. We want to have as many things with a formal charge of 0 as possible. The formal charge of the oxygens with a single bond is going to be the number of valence electrons minus the number of bonds minus the number of unbonded pairs. And that gives us a formal charge of -1, and we have 2 of those. The formal charges of the sum of the formal charges in our ion have to add up to the total charge. So plus 1, minus 1, and then there's 2 of those. So our overall formal charge is -1, and that's okay because nitrate has a charge of -1. If we were going to try to optimize formal charges more here, we might try to make more double bonds to oxygen, but nitrogen being in the second row cannot accommodate more than 4 bonds. However, we still have to, we need to identify if there are possible resonance structures. When I chose this oxygen to borrow electrons and put a double bond, I could have done this one, or I could have used that oxygen. Anytime that's true, there's generally going to be resonance structures. So the resonance structures for this ion are going to have double bonds in the other positions where we could have initially chose to. So that's one. And then we could have also chosen to put the double bond here, and that is another resonance structure. Because nitrate is an ion, we enclose it, and also because it has resonance structures, we enclose it in brackets, and then we put the charge on the outside. We also need to talk about the shape of nitrate. Nitrate has 3 electron groups. Each of the oxygens with a single bond is an electron group, and then also the oxygen with a double bond. We count the double bonds because they go to the same atom as a single electron group. So there's 3 electron groups. The furthest they can get apart is 120 degrees, and so our shape is trigonal planar. And the angle between the bonds is 120 degrees.